Thanks. And thanks to the organizers for having me here, and to Andy for giving my instructions, which were to talk about kind of new approaches and technologies, advances, and how we go about making observations in the ocean. Primary collaborators listed here: Jason Goback and Ringo from my group. Lee Freitag is our main collaborator at Hui. He and Zaycom's group have been instrumental in what we've been doing. I'm going to talk about infrastructure, some work on ice shelf cavities, the Dotson mission that Catherine mentioned, a little bit about mobile observing networks, then Arctic Argo. But I'd like to start by just doing this brief introduction, because this team that you see down there in the bottom is really important. That's our research group. We're a combined basic research and technology development team. All that goes hand in hand for us. We actually talk about what science we want to do and what instruments we're developing. We're pretty platform agnostic, except these guys are kind of our babies. We're the developers, one of the 3 production glider platforms in the community, long endurance gliders. But really, we'll pretty much use anything that we feel like gets us to where we want to be. Work all over the world, and so we kind of carry those lessons to our Arctic work. But how do we think about this, right? I'm a physical oceanographer, right? So I tend to think about things in terms of scales. Spatial scales, time scales, how quickly we need to resolve things, right? Do we need a measurement every year? Is that enough? Do we need a measurement every 5 minutes, right? Does it have to be over the entire basin, or can we focus in on something? Are we doing a process study, or are we looking at kind of large-scale changes? On top of that, we do a lot of work for like the US Navy or different communities, right, where it's actually bringing back observations that are going to feed models. So there's some consideration at times for whether or not you need data in real time or something that resembles real time. Sometimes you can't have that, right? Sometimes there's a lot of latency. There's a lot of expense involved in getting data back in real time. So these questions all come into play with how we think about these things. It kind of sucks because the physics are nonlinear, right? So all the scales interact. So at any given time, we've got to be measuring a range of scales. We can rarely concentrate on a single scale. And it's even more true for biology and biogeochemistry when we get to there. Their problems are worse, right? They're much harder. We concentrate primarily on autonomous platforms, so things that are nimble. We do a lot of ship-based work as well, but really the question is, right, we want persistence, we want them to be scaled, we want to be cheap, we want them to be nimble and flexible, we want to be able to have sustained networks of these things. And there have been real revolutions in how we go about using small-scale robotic platforms to achieve that. So because I wasn't sure how much people understood about the way we go about making measurements in the ocean, I thought I'd do a little bit of leveling here. Traditionally, we do this in ships. Right, we drive around in ships of all different sizes with our instruments on cables, and we make measurements. We collect water. Sometimes we use sensors. We send things up into the atmosphere. But fundamentally, that's like driving around in a car, right, from here to San Francisco with a thermometer on a balloon, letting the balloon go up and down once in a while, and then trying to calculate the heat content of California for the measurements you've collected. Kind of hard. Ships are great, though, because we can do a wide range of measurements on them, and they move at the astounding speed of 10 miles an hour, which for oceanographers is really fast, right? So we can actually make what we think about as being synoptic measurements or snapshots of 3-dimensional cubes of ocean with a ship. As you go into the autonomous platforms I'm talking about, I'm just showing you 2 of many right now. If you haven't heard of Argo, it's a network of profiling floats, 4,000 of them in the global ocean, going up and down once every 10 days. Over the past 20 years, it's revolutionized how we do some aspects of oceanography. Let us make calculations we've never been able to calculate before, access time and space skills we've never gotten to before. But they're little floats. They're kind of, that size, right, the tube. And they profile up and down over the upper 2,000 meters of the ocean, or the upper 6,000 meters sometimes now. Light payloads, but missions as long as 5 years, drifting. The novelty there is they just drift, right? You deploy them and they distribute themselves, and it doesn't matter where they go as long as they're distributed. Gliders, on the other hand, have missions that are typically anywhere from half a year to a year, as long as 2 years, really. That's what we've managed. They move at the astounding speed of half a mile an hour, half a knot. But they can do that over very long periods of time. So they can navigate across very long spans of ocean. We can make sections that go across fronts or go across eddies. Fundamentally, they measure at very fine scales though as they do that, right? So instead of being distributed like a ship, they're measuring along a line, and they're making very fine measurements along that line. So we'll see an example of why you would choose one platform over the other later in the talk. So in addition to that, in the Arctic and the Antarctic, right, we rely a lot on surface-mounted platforms. Got this big plate of ice, you can take advantage of that by putting things on the ice. The classic is the International Arctic Buoy Program, which are just a lot of buoys that have been placed onto the ice, often just kicked out of airplanes, right? And so they're just sitting on the ice, they measure surface pressure, they might measure air temperature. Not a lot else typically because they get expensive and they're more involved to deploy if you do that. But you can get large distributions of them. That's a recent snapshot of the buoy program. Right? You'll notice there are big holes like in the Russian Arctic, right, where nobody puts instruments out right now. So even though it's distributed, it's measuring half the Arctic. Another example are profiling instruments. So now that we're getting more complicated, right? You go out, you drill a hole through the ice, you extend something on a tether. The ice-tethered profilers have been kind of the marquee platform for a number of years for us, right? Where they've got a profiler, moves up and down through the upper 500 or 800 meters of the water column, making CTD profiles multiple times a day or maybe once a day, depending on how you're using it. There are lighter weight versions of this, like the up-tempo buoy, which is just a lighter measurement suite. It's cheaper. These are heavier logistics to deploy, right? So that's a recent picture of those buoys. Not many of them. You'll see a picture of Global Argo a little later, right? And this already looks pretty sparse. It looks really sparse when you compare it to what we have. But that's really changed what we know, right? It's been a new look at the ocean, new look at the Arctic Ocean. Atmospheric measurements, untended atmospheric measurements, are still really difficult to make. Occasionally, we can make some very basic things for a short period of time. But the more involved measurements, say what you might want for a surface energy balance, are really tended operations, like typically based off of the ship. Haven't figured out how to do those in an untended way yet. So one thing about modern robotic instruments is they rely on satellite services, right? The reason why we have gliders and floats and they can be all over the world, or these surface-mounted instruments, is because they can access GPS and an iridium cell phone. GPS lets you know where you are, right? You carry it in your pocket, the instruments carry it too. The iridium service allows us to bring data back in real time. And most importantly, it allows us to bring data back without getting the instrument back. Right? So you no longer have to go fetch the instrument, which is a very expensive endeavor. Putting out there's one thing, getting it back is a completely different thing. And it's also very risky. So how do we do that in a case where the surface is denied, right? You can't get to the surface most of the time. We do navigation and some communications with acoustics. Same way, the middle is an example. That's the first time we did this, which was really in about 2008 in Davis Strait at the southern end of Baffin Bay. It's part of a long-term observing system we've maintained there for 20 plus years. But we learned to run gliders under the ice in Davis Strait by using acoustic beacons and having the gliders basically calculate the position of multilaterally from the transmissions. You know where the beacons are, you know what the travel time is, right, between the transmission, how long it took the transmission to get to the glider. You can draw a range circle. When you can have 2 or 3 of those range circles, you can calculate a position. So the current state of navigation communication, we laid out a roadmap in 2006 to get us to where we are today, and we're pretty much done with it. We use, from high frequencies to low frequencies, 10 kilohertz to exchange data at the amazing rate of something like a 300 baud modem, if anybody remembers sticking your phone in a modem to move data around. But it's high speed for stuff that goes through the ocean. We use a range of frequencies in the 1 kilohertz range from 260 to 925 hertz to do modest ranges in the Arctic and the Antarctic. Think ranges of 100 to 500 kilometers from a beacon. That's good for doing something like Davis Strait, pretty awful if you're trying to insonify the central Beaufort Sea or the entire Arctic or any portion of the donut that is the Antarctic, which is a harder problem. And we now have 35, which is the new thing. I'll talk more about that, but that's Previous experiments in the Arctic demonstrated you could get across the entire Arctic at those frequencies. So we knew that would work. The trick was getting sources and getting things set up. We now have those kinds of sources available to us and working. So now we can insonify things like the entire Beaufort Sea or eventually the entire Arctic and have underwater GPS in the region. So I'm going to back up a little bit and talk about the DOTS mission, and then we'll progress to other more complicated things. This is something we did a while back in 2018, and we are still working up the data, but it will get there. We went to the DOTS and Ice Shelf funded by the Allen Foundation, who was willing to take a big risk. This is one of those things that could have been a gigantic smoking crater, or it might work. Turns out it worked. The idea was we already knew how to run gliders and floats under the ice. Could you do it in a cavity without actually putting anything into the cavity, any of the acoustics? So we put 3 sound sources in front of the shelf in the open water. You can't see them in the mess that's, well, they're the white triangles in that mess, right? The DOTS and Ice Shelf is to the south. We ran gliders into the shelf. So this, let's see if this works. Not really. This region that you see here, right, that's the DOTS and Ice Shelf. We took 3 gliders and we ran them into the shelf. James Gurdon took 4 floats, put them in on the inflow, let them basically hot air balloon in on the inflow profiling, change the density surface, and have them come out on the cold outflow. Gliders operated for 14 months, so 2 summers. 38 sections across the shelf face, so across the front, and another 24 sections going deep into the shelf, and you can kind of see these cross patterns here. We started shallow and then got braver, and then we started doing transverse sections as well across the cavity. Some in the first summer, we ran out of time to figure out the algorithms to get the gliders inserted into the shelf. It's a little tricky when there's a horizontal obstacle. We're not used to dealing with those. So we stayed on the outside through the winter and just made sections under the sea ice, but across the face of the shelf. And then the following summer, we went back and did more sections under the shelf until the gliders ran out of gas. 240 kilometers, the longest survey that we had inside the interior. So 240 kilometers of track running around the interior of the cavity, and 70 kilometers from the face. The floats all came out. One of them came out a different ice shelf, which is interesting. Weren't really aware that there was a connection, but there clearly is since the float made it through. 90% of the receptions actually were heard by or 90% of the transmissions were received by gliders, which is pretty remarkable. No pattern, no dead zones that we could discern inside the cavity. That will vary depending on cavity geometry. Dotson's a simple geometry, intentionally chosen because it was simple. But in this case, pretty much the entire cavity was navigable. Right? We could geolocate inside the entire cavity. You get cool things like these sections that go pretty far into the back. You get things like sections that go into the perceived dirt. What that says is that the bathymetry that was inferred from gravity measurements is wrong, very wrong. Right? I mean, the glider is merrily going along through what should have been sills and other features without a problem. It actually went into some basal crevasses, which aren't shown here, but we had some interesting excursions through there. This was one of the issues getting in, right? Figuring out how to navigate past that. We could do it by hand. We came up with an algorithm for doing it autonomously, but we were cowards. We decided not to risk it through the winter with the vehicles we left. Some interesting things, right? There wasn't that much warm water actually in contact with the bottom of the shelf, at least in the measurements that we collected. No really well-developed mixed layer at that interface. And then you'll see it in a second, but the outflow in what we measured was really confined to the western boundary of the cavity. You get things like this is a composite of a year-long or 14-month-long record of measurements in front of the cavity. Right, so actually outside the cavity, but directly in front of it. Kind of we just put together this record to be more or less in the middle there. Just see what that looked like. And you see fairly radical changes through the course of the year. And the thing that we're working on right now is we have 38 sections across the face, right? That look like this, and you can see the warm inflow and you can see the cold outflow on the other side. You can see enhanced temperature variance right at the level of the shelf bottom. And you can also do an inverse. You can try to do a mass conserving inverse to look at the heat transport in and out of the shelf, which is what we're currently trying to, it's the last piece of what we're trying to do in this analysis. But those are the fun games you can play when you've got these time series of records, right, and you've got enough data to work with. So let's flip back to the other poll. We'll spend the rest of the time here. We've worked in a series of Office of Naval Research Arctic initiatives, starting with the marginal ice zone, looking at melt. With the spring, the idea was to go up there fully autonomously, without ship support initially, and get in there before the melt began and run the experiment, looking at the changing dynamics as you walk back from the ice edge and from the open water through the Miz back into the pack, right, over the course of the melt. Seastate looked at the freeze-up period, more ship-based, but kind of looking at the freeze-up period, and was really focused on the role of surface waves in modulating the freeze-up. SOTA was looking at the change in vertical stratification over the course of a year, over an annual cycle. And then what I'm going to talk about is the Arctic Mobile Observing System. These were all science-driven programs. AMOS was a technology-driven program, which was really trying to get us to a point where we could take all these individual pieces that we had, surface elements, floats, gliders, AUVs, and network them together in an integrated observing system that you could scale. Right? You could do different things with it. You could do process studies, you could do large-scale studies. So this is AMOS. This is the cartoon, because every program's got to have a nice cartoon. The nice thing about this is it's actually all real and working, and I'll walk through that in a minute. But this is composed of gateway buoys, which are the ice-based systems you see at the surface. They're mainly meant to be foam buoys to allow instruments under the ice to get data out and back to home. They also provide some navigation, and in the case of the big ones, they provide a platform for atmospheric measurements. We focused on these 35 Hz sources, 2 of them to provide navigation throughout the Beaufort. We deployed a bunch of 925s because we're cowards, and we knew the 925s worked, and we weren't totally confident about the 35s initially. So there's redundant navigation in the system. In this, we throw gliders running through the system, profiling floats at one level, at a low level in this program, and then I'll talk about the Arctic Argo push in a minute. And then another group, Lee Fartag's team at Hui, was playing around with a REMA 600 AUV. Initially just learning how to operate it in the Arctic. Eventually the idea was they wanted to be able to dock it. So quickly, that's the 925. The point here is it's small and cheap and long-lived. We can get about 3 years out of that. That's the 35. That's about the size of a small car. It is not small. It is not cheap. It eventually we'll be able to get a couple of years out of it. I think right now we're doing about a year on that system. And you can see they're deployed on one side of the Beaufort. So this is transmission reception, but the point here is that the largest separation we've had is 700 kilometers in this system, and we get good reception out to 700 kilometers there. Not as good deep, and that's something we're working on. It's a signaling issue, and we think we understand how to improve that. We started with a very sophisticated detector. We've implemented a low-cost, low-power detector that's more generalizable for Argo floats, other platforms, and that detector is providing the same performance as the more sophisticated one, except it can't do communications. It only does navigation. 2 gateway buoys, the small one, again, light, small, low cost, put them out in quantity. but they're not really intended to survive a melt-out freeze-up cycle. The big heavy ones, huge, hard to manage, but they can survive years in the Arctic drifting. They're meant to, and we've had one operating for a while. Those are Sarah Webster's baby. She's been working with a group that includes Chris Cox and Jeremy Wilkinson and company to make atmospheric measurements, test different atmospheric sensors off here because you've got a lot of power available and it's high up out of the ice, so it's a little more protected. Ice mass balance, and then the idea was to eventually be able to dock AUVs to that. Speed up a little bit here because I think I don't want to run out of time. So what sorts of things do you get out of this, right? You've got this whole system. The idea is to be able to have gliders that collect data, maybe talk to floats, bring the data back to the phone booth, transmit it back up, take new instructions, go do different things, right? We'll start with the gliders, right? This is an example of one of several year-long missions we've had up here. We've had one last as long as 2 years by hibernating part of the time, letting it drift and then reactivate. But because we're out there for a while, right, we pick up a number of these little Beaufort eddies that you might expect to see, enough that we're starting to do censuses of eddies as part of the analysis. You can see the glider track there where we kind of deployed it in the center, and for 196 we eventually had it come south for recovery. Often we'll just kind of park in the center after the glider's done doing whatever else we want it to do. Might have to do little sections. Part of the lesson is that we've gotten pretty good at getting gliders to survive the winter. About 2/3 of the gliders make it through a full season. We've gotten less good at actually getting the gliders back at the end of the winter because it turns out operationally it's hard to get up there at the right time to get the vehicle back. The vehicle may be on the surface and ready to be recovered, and you may be months away from being able to get a ship to it. Right, so the obvious solution is you come off station and you get closer to Reykjavik, and you're easy to pick up, but you lose data when you do that because it takes a while to get there, so it's a trade-off, right? Data or vehicles back, and often the data is worth more than the vehicle is. So this is kind of the money slide. This is the whole system working, and it looks really simple, but I'll explain. This is an example of the system working together where the navigation's got to work, the communication's got to work, the autonomy has to work, everything has to work together because we've deployed a gateway buoy over here. In this case, a heavy. We've done it with lights as well. It's drifting on its own. This whole area is ice covered, right, in the pack. We stuffed a glider through a hole in the ice about 100 kilometers away. So we're not going to hear from it again after we've pushed it through the hole. The glider's been told, go find the gateway buoy, right? Go find it. When you find it, tell us what you've seen and we'll tell you what to do next. So it takes it a while. Color is time. It takes it about 2 weeks, 3 weeks. It eventually rendezvous with the gateway buoy. Co-samples with it for a while. Follows it. Eventually the gateway buoy drifts out of where we want it to be. So we send the glider off on a different mission. It's uploaded data, it's downloaded new commands, right? It's responded to the new commands. This is why I say it's a simple plot, but it is all the elements that were meant to be in the system working together the way they're supposed to. We've now done it multiple times, so we know that it's not a fluke. So let's talk about the Argo part of this. I didn't talk much about the floats in that system. We've been able to offload data from floats, but it's not as easy to do. The bigger push has really been to try to get Argo in a position where we could deploy large numbers of floats in the Arctic and the Antarctic, and where we could navigate them acoustically if we wanted to or needed to. First point, why? Why Argo floats in the Arctic, right? Why not just gliders? Why not just the platforms we have? In the left here, you've got a comparison between roughly the same period. Glider profiles, roughly 30,000 of them. Argo float profiles, roughly 2,500 of them, so far fewer. But you notice something immediately, right? The floats are what you want if you want to be able to make maps of big areas. You want to calculate the freshwater content of the Beaufort? Gliders are not a good idea. Floats are a great idea for making maps like that. They're cheap. You can put in a lot of them. They do what you want them to do. Why in the Arctic? Because the ice-based instruments that we currently have just aren't dense enough, and we're not going to be able to get them to be dense enough because of the cost and because of the logistic overhead of getting them in. So here you've got an example of the Arabian Sea for kind of a 1-month period in Argo floats, and the Arabian Sea is sparsely populated with floats, so it's not even a good place to look. And you've got an example of a 30-day period with our profiling platforms in the Arctic, which doesn't look so good, right? If you're trying to make a map of freshwater content with that, you're in trouble. So what you end up doing is you end up averaging over a much larger period of time to make the maps. And there's been some great results produced by doing that, but they are smearing over larger periods of time, and you might like to have more granularity, particularly as we try to attribute changes that we see and associate them with things like export. So we adapted the Teledyne Apex float as part of LAMA's program with the navigation capabilities. Working with Dan Rudnick's team at Scripps, we've done this to the Solo 2 now. So that's two of the major platforms. With the Solo 2, with the Apex, we integrated the more sophisticated nav system. With the Solo 2, we've concentrated on this low power, low cost system, which we want to be generalizable through the community. That has worked really well. We've got 3 in the water right now. One of them was put through an ice hole during the Navy ice camp in 2024. 2 of them were deployed in the summer when we were up there for AMOS work. This one in the red circle is the ice camp float, and it's more interesting right now because you can see the acoustic track in the colors here. Color is time. Blue is when it was first deployed through the ice. It first surfaces in the green right there, and then you start to see a solid line over the axis, which are the interpolations between the GPS fixes. So you can start to compare the acoustic fixes with the GPS. That is unfiltered, very simple processing to get that track. It's nice and smooth, which is reassuring. It's positioned every 4 hours, so we're actually getting the drift track. It does things you expect it to do, things like the loops. And it matches the GPS track pretty well. There's a little offset, and we think we understand why that is. It has a lot to do with the geometry of where that float is relative to where all the sources are. So probably something that we'll be able to correct for eventually. It's hearing both 35s and 925s at this point. We'll put 12 more in this summer, and we'll put 14 more in 26. Once we hit that, and the Beaufort will be up to Argo density in the central Beaufort. And the intent is to continue that and actually spread the system into Baffin Bay, which is the next place that we intend to go. Working with Norwegian and German colleagues to spread the system to other parts of the Arctic as well. This is an example of the upper 400 meters of the record from that first float. The point here is you get very nice resolved data, temperature, salinity, sound speed. You see a shift in the vertical structure in September. It's don't want to read too much into it right now, right? Because the float is drifting from closer to the slope into the interior of the Beaufort, and there's a change in where the Pacific water sits as you drift. That change is a little more abrupt than I might have expected from that shift. The bowl is a little more gentle, but as we get more data, we'll kind of be able to sort through what's time and what's space. Might actually be on time. So, where are we at? Integrated onto 2 of the major float types. Steve Jane is integrating onto the MRV Alto floats. We're going to work with NKE to integrate onto that line of floats as part of the Baffin experiment. And we're packaging this low power detect system with an external hydrophone so people will be able to stick it on anything they want. The idea is to generalize the system, make it readily available to the community, and make it cheap. Argo cheap, hopefully, eventually. We're trying to expand the acoustic infrastructure. That will only happen through international collaboration. So we're talking to colleagues at North Polar, right? Talking to colleagues in the Antarctic about interest in using this. It was a lot less interesting when it was a 1 kHz system. It gets more interesting at 35 because you can stand off the continent and give navigation to a larger scope of the ring, right? And a couple lessons to close with, and they're mainly tech development lessons at this point that I've listed here. My business comes from somewhere else, but I think we benefit a lot from having the science and the technology development really tightly tied in a single team. It helps me understand what we can do. It helps our technologists understand where we want to go so we don't get a lot of drift in either direction. We're really focused on systems of complementary platforms, so it's not, this can all be done with floats, this can all be done with gliders, right? It's all how you put systems together for a particular goal. The science goal comes first, and then you design the system to get there. For us, it's been operating at scale. So the redundancy of lots of inexpensive platforms that are fairly simple, but cheap enough that you can afford to lose. Some significant fraction of them has been important because they go away. Right? Things go wrong, platforms go missing, things don't return data. So being able to deploy things at scale has been key. Lightweight, inexpensive, simple, flexible, lots. Flexible logistics have been really important. The ability to hand people things and have them deploy them for you or recover them. To not be tied to big ship logistics all the time. So those huge sources require a large ship. There's no way around it. The floats don't, right? They can be pushed out the back of a plane. And then the last is this real value in having the ability, and this came from the Arctic Mobile Observing System program, but the ability to go up year after year and just try things and repeat that trial and error process consistently has been invaluable, and even more than its value to the hardware and software development has been the value for understanding how you do things, what we call concept of operations. So it's one thing to get the hardware right, it's another thing to get the software right and have all that working. It's a completely different thing to understand that, oh, yeah, we can't get up there to get the gliders back consistently in the summer when they come up, right? We need to rethink how we're thinking about that whole thing if we want the hardware back. There are other little things about how we work when we do things or how we sequence things, right? How we plan that have been lessons that would have been hard to think out without actually going through the motion of doing some of them first and seeing how it worked out. And I will leave it there. Thank you.
Thank you, Craig. Questions?
Thank you for the great talk. I'm wondering how much, I mean, you have the sound source, right, to communicate with the gliders, but how far can they go? And at the same time, I believe there's a temperature minimum zone that the sound wave kind of propagates in that. Prefer to propagate, there's some depth level that sound wave propagates more, I mean, easily. Is that right? So I'm just wondering how that interface, how that influenced that.
So I'll do the easy one first, which is the 10 kilohertz for data. You have to be really close. It's a few kilometers. So you've got to get the platforms close to each other before you can trade data at rate. In the Arctic and the Antarctic, and most of the environments we're talking about, everything's surface ducted, which means there is no sound channel. Things come right up to the surface, they reflect off the ice bottom, and they just keep doing that, which is the problem with using sound at a kilohertz, that 260 to 925 range I showed you, right? It's the reason why we only get 100, 150 kilometers in the worst case in, say, Davis Strait or some parts of the Antarctic, because the sound decorrelates when it reflects off the ice. At 925 broadband, we can transmit a little bit of data. So we can transmit a command or a position, which is the reason why the source can drift with the ice. The reason why the 35s are special is because it's a very long wavelength. It doesn't really seem to care that much about reflecting off the bottom of the ice, and so it can go transbasin, right? You can hear it across the basin. The Beaufort is great because it does have a sound channel right now. Pacific water creates a small sound channel that we can take advantage of. It's shallow, which is kind of unfortunate. It'd be nicer if it were a little deeper, but it's there. It gives us ranges of 500 kilometers. I didn't show you the 925 results because it's just too much, right? But if I showed you a 925 plot, it wouldn't look that much worse than the 35 hertz plot that I showed you, because the ranges have all been, 700 kilometers maximum for the system. We know we can get 2,000 off the 35, and I know that we won't get 2,000 off the 925. It maxes out at about 500 in the Beaufort. And that, we think that soundscape is going to change over time. And it would not be surprising if 50 years from now there is no sound channel.
Thank you.
Hey, thanks for that talk. This is a really quick question, and I think I just missed it. But I was curious, with those Dotson observations, is that one snapshot, or is there? Do you have like a series of snapshots over the course of some amount of time?
So the set the plots I showed you at the face.
Yeah.
That's an average.
Okay.
Of 38 sections over the entire year. We have 38 sections. When we do the inverse, the idea is to do them section by section.
Awesome. Thank you.
Yeah, we have quite a few sections in front of the face and quite a few in the interior.
Thanks for the talk. That's super cool. I have two questions on the Argo part. One quite technical. With the float you've been using so far, are they all able to cross the buoyancy barrier that you have with the strong certification? Because I thought they were kind of a loss of profile because the float were not really able to reach the surface and cross the strong certification. Is that still the case, or you don't have any problem there?
So the Apex floats struggle. We chose the Apex floats for Amos because they were the floats that we could get. We had a branch of the source code that we could work with. We can't develop unless we have the source code, right? And we don't particularly like working with companies for NRE, and so it was easier for us, but it was not a good choice. The Solo 2 seems to be doing pretty well. We'll see how it does this spring when it starts to come up. It's got a little better DV over V than the Apex does. The NKE floats look like they will be a reasonable choice. But yeah, you're exactly right. We have the struggle, for example, with our current generation of gliders, that there are times when they basically are trapped below a very buoyant layer, and then you've got to wait until it mixes a little bit, right, until the water becomes a little denser and you can surface.
Can I have a second question? I think it's more generic. I agree that Argo is to some extent the way to go, and that complement nicely ITPs, but we're still basically sampling the same region, and we're not going to get much on the shelf, which is like a large part of the Arctic. What would be like? What would you think would be the way forward to get some kind of autonomous platform for the shelf as well?
So this was the subject of a rankers debate at the last Argo steering team meeting. Argo wants nothing to do with the shelves. You probably know that. At the same time, those of us who work in polar regions argue that the shelves are a key part of the story. There's no reason why you can't use a float on the shelf, right? The Argo argument is twofold. One is that it dilutes the core mission, and they see it as a waste of money because they're basically counting dollar per meter sampled, right? If your profiles are quite shallow, that's a bad deal because there are not very many meters sampled. I think most of the people in this room would argue that those are really valuable meters, and that they would be worth 10 times the dollar value of a deep profile. And so it's a difference of opinion. There are some inexpensive float designs that are being floated. Some of them are being tested at APL. MRV's got a size tube float they call the Alamo, which Steve Jane uses a lot. It's shallow sampling you could use on the shelf. So there are tools that could and should be used, and I think we can do this without being part of global Argo, right? Whether or not Argo actually wants to go on the shelves, the polar communities can put together a system and start sampling them anyway. And that may be what we have to do.
Okay. I mean, I tend to agree. I deploy Argo float and that profile 200 meter. But I think if we cut that deployment from the whole Argo array, it's going to be a miss and a loss for the whole community. That makes no sense either. So I think we need to make a case for Argo over the shelf and explaining what that's still cheaper than any other measurement and that's still super valuable. So, but yeah.
Having had this discussion recently, I think it's going to be an extremely difficult sell. Right? You've got a critical system for the larger ocean community, which is much larger than we are. Some of us are part of that community. I am. They're not likely to back down in a time when the system is under threat. So I think it's probably easier to make an argument for moving forward as our own community to do some of this. And eventually, if it demonstrates value, if things become less threatened, right, we may come to a point where those systems can come together and have some agreement about this. And the same discussion happened with biogeochemical Argo, right? The argument about whether biogeochemistry should be allowed into the tent or not. And it has been. It's now part of the one Argo concept, but it wasn't at the start.
Hi, I have a couple technical questions. Yeah. Can you just say what the horizontal footprint of the acoustic data is, and also how deep can it see before it gets attenuated?
I'm sorry?
For the acoustic data that you're showing, so you gave the frequency, so you can get the vertical resolution, but what is the horizontal resolution of it in general? And then also, how deep can you see into the water column?
The acoustics are just being used for navigation, so essentially you've got an acoustic beacon that's transmitting a sweep, and you're on a schedule, and a platform that's listening for the sweep, and all it does is write down the receive time.
Can you use it to look at the temperature structure?
No.
Why not?
Right now, because we're not transmitting a signal that's appropriate for that. We could transmit M sequences and do this for tomography, and that's been a debate within part of the tomography community, right? Because right now they have some of these sources in the Arctic that are transmitting very long M sequences for tomography, for basically taking the temperature of the integrated pathway. The signals are too expensive to transmit, and they're too expensive to receive energetically to be used for navigation. You could mix up the signals. You could use shorter M sequences. You could interleave long M sequences with short navigation sweeps, right? So eventually you'd like to get to a point where you're dual use in this, where you use it for navigation and tomography. You could imagine a great world where all the autonomous platforms are also tomography receivers. And so now you've got a huge number of pathways available to you. Not as good as the well-surveyed pathways of the tomography moorings, but there's a particular quality in having large numbers, right? So yeah, that's where we would like to get. We're not there now.
Thank you.
Yeah. We have time.
Yeah. Thanks, Craig. Could you go back to the slide just before this one, please?
Sure.
We had a nice talk this morning from Eric trying to help us understand why you get these variations in CDW thickness on interannual to decadal to centennial scales. This figure seems to show we get many hundreds of meters variations in CDW thickness in 1 year.
Yeah.
Do you want to comment on whether we're aliasing a lot of variability because we're only there in summer outside of measurements?
I'm sure.
Yeah.
Yeah, I'm positive. That's the whole point of being able to do something like this, right? Is to at least understand what's being aliased, and better yet, to be able to start to resolve some of it.
Do you think, I don't want you to answer this here because we're almost out of time, but do you think you understand what's being arised?
We haven't concentrated on this part of it yet. You can imagine a number of processes that might pulse warm water onto the shelf, and they could be quite episodic.
One question is it feasible technologically to have the same kind of resolution of measurements on the same amount of Argos in a certain sense in the Arctic and elsewhere, or there are limitations in terms of the fact that the communication and the position is done differently? Does that limit the amount of instruments we can deploy?
You mean, you're asking if there's a limit to the number of instruments you could deploy in polar
Essentially,
regions?
yes.
No, not really. The limit is probably platforms to deploy from, right? Argo, a lot of the work in Argo is finding ships of opportunity to get platforms into regions that you need to populate. And a lot of work in something like IABP, the Ignatius and others do, is finding planes and ships that are going out to distribute buoys, surface buoys to the Arctic. We're going to face similar problems when we try to start spreading the platforms out more broadly in the Arctic. We've started, didn't show up, but we've started to play around with a really simple autonomous deployment mechanism, which is essentially hanging a bunch of floats from a 2x4 on a cable in the ice, and having them on a berm wire, and nearby having a little iridium modem and a hydrophone that sticks down so you can trigger the berm wires. And then you let the floats drift around with the ice, and when they're somewhere where you want them to be, you just tell it to release one. As a cheap way of getting floats to more places, laying the ice, distribute them. So there may be tricks like that, but yeah, the data is all still coming back mostly by finding open water. We can get small volumes back acoustically, but for a float, that requires the float to magically get near one of the phone booths, which sometimes happens, but it's a big ocean. There are not many phone booths and there are not many floats, so you can imagine what the odds are. Gliders can find floats and pull data off, but that's pretty laborious, and you'd have to ask why you're doing that. Right, it's a very expensive way to get the data from the float. So better is to just put out a lot of floats and wait for them to come up and transmit the backlog data.
All right, one more question. Rebecca, do you want to come up?
It's not particularly well kind of formulated question, but do you think that the current state of technology is sufficient that all cavities could be mapped, all subice shelf cavities could be mapped?
Sorry, could you repeat that?
Do you think that the current state of technology and development allows us to map all cavities around Antarctica?
All is a big number.
Then slightly different question. What would require us to get to the point that all cavities could be mapped?
Much cheaper platforms. One, it's some of the issues that we face are just the cost of getting things out there. Right, and there's no good way around that. That's not going to get cheaper in the end. That won't get less expensive. And then the last piece to it is, what I showed you is a particularly simple cavity. Right? We chose it over Thwaites because it was simple, and we didn't want to make things any harder than they were already going to be. I don't know what that's going to look like when we go to a more complicated place. I'm kind of curious and waiting to see. It's probably going to be a lot more painful.
Okay, thanks.
All right, thank you, Frank.